In this video, we'll talk about differential equations, first-order differential equations that are separable. So let's just recall that a first-order differential equation, first-order differential equation is an equation that relates a number of things. Okay, that relates uh, a derivative of a function with respect to a variable, the function itself, and the independent variable. So this is the independent variable. Right. So that's the independent variable. This is the dependent variable. And dy dt is the derivative of y with respect to t. And sometimes you might see dy dx and then y and x. So it's a relationship between these three objects. Now, separable equations are equations of the following sort. So let's take an example. Suppose I have 3y squared over t squared plus 1 dy dt equals 1. So the idea behind a separable equation is that we're going to treat dy over dt as a fraction. And so you can actually dissociate the dy and the dt by multiplying both sides by dt. So for example, if I multiply both sides by dt, I get 3y squared over t squared plus 1 dy equals dt. And the idea here is to separate all the y's to the left, okay, to the left, and the t's to the right. And so I can get 3y squared dy equals t squared plus 1 dt. Now we have a dy on the left and a dt on the right. We can integrate both sides. And we're going to talk about a little bit about why we can do that in just a little bit. But let's take the integral on both sides. This is the indefinite integral. And what we get is y cubed is equal to t cubed over 3 plus t. Now remember that when you integrate, you have to add a c. And technically, you should have a c1 here and a c2 here. But because you can move this c over here and get c2 minus c1, you really just have to do it on one side. So when we take the integral of both sides, one side gets the c, usually the one with the independent variable, and the other side does not. Then integrate both sides and then solve for y. And here, y is equal to the cube root of t cubed over 3 plus t plus c. So this is called the general solution to the differential equation, okay, equation above. Now, one could be asked to check, okay, check this result. So how do you go about checking this result? Well, let's take a look. The result says, okay, the original differential equation says 3y squared over t squared plus 1 dy dt. So using this particular y, let us figure out whether or not it's actually equal to 1. So here's 3. Now the y is given by this object right over here. Now this is to the 1/3 power, right? And then I'm being asked to square it. So it's actually going to be to the 2/3 power, right? Divide by t squared plus 1. And then I need to take dy dt. Now let's remember that y can also be written as t cubed over 3 plus t plus c to the 1/3. the derivative will be 1/3 t cubed over 3 plus t plus c to the negative 2/3. And then I have to take the derivative of the inside, which is t squared plus 1. And you notice how this cancels with that, this cancels with this, and then that cancels with that, leaving you with 1. So indeed, the solution is correct. And that is the general solution for that differential equation. Let's consider another example. Suppose we have the equation dy over dt equals e to the t minus y plus 3. Well, in this case, let's do the following. Let's write this as e to the negative y, e to the t plus 3. The reason that we do this is that we want to separate the y's and the t's. So now let's move all the y's to one side and move all the t's to the other. So multiply both sides by e to the y and by dt. This puts the e to the y on this side and then puts the dt on this side. Now we integrate. So let's integrate both sides. On the left, you get e to the y. And on the right, you get e to the t plus 3 plus c. And to solve for y, simply take the natural log. So when we take the natural log, we get y equals the natural log of e to the t plus 3 plus c. And this is the general solution. Now, you may be asked, verify that this solution is correct. So let's go ahead and do that. How do we do that? Well, we take the original equation, say right here, and we're going to check left and right sides and see that we get the same thing. So the left-hand side is dy dt, and here's my y that I've just computed. The derivative of y in terms of t is 1 over e to the t plus 3 plus c. Remember that the derivative of log is 1 over what follows. And then I take the derivative of the inside by chain rule, which is e to the t plus 3. So I get e to the t plus 3 divided by e to the t plus 3. Now let's check the right-hand side. The right-hand side says this, okay? So e to the minus y, e to the t plus 3. And let's see what this yields. Now, what I need to do is I need to plug in the y that I solved for and put it right there. So I get e to the minus log of e to the t plus 3 plus c times e to the t plus 3. Now, when you have a log and an e right next to each other, they cancel out, but they can't cancel if there's something in between. So here we have to use the rule that r times log of u is equal to log of u to the r. The r goes into the exponent of u. So this -1 can go into the exponent of this piece right here. So it's e to the log of e to the t plus 3 plus c to the -1, e to the t plus 3. Now the e and the log can cancel, giving me an e to the t plus 3 plus c to the -1, e to the t plus 3. The -1 puts everything downstairs, so I get e to the t plus 3 plus c. And you notice that these two expressions are exactly the same, so our differential equation is solved, and we verified that it is correct. Let's now take a look at this problem. dy over dt is equal to 1 minus t plus y squared minus ty squared. Now this one is a little bit tricky. It doesn't look like you can do much with this, but if you stare at it long enough, you'll realize that you can actually factor this. This can be factored into 1 plus y squared times 1 minus t. Now, this puts us exactly into a separable environment because I can divide by 1 plus y squared, and I can multiply by dt. So I can move all my y's over here, and I can move my t's all the way to the right. And so now I have all the y's on one side and all the t's on the other side. I'm in a position to integrate. And let's see what I get. The antiderivative of 1 over 1 plus y squared is arctan of y. And the antiderivative of 1 minus t is t minus t squared over 2 plus c. To solve for y, you just take the tan of both sides. So the tan of the arctan cancel each other out, leaving just y. And then I have the tan of t minus t squared over 2 plus c. So this is a very quick general solution. We're not going to verify that this is the solution. The calculation is a bit intense, and we will dispense with that. You can check it on your own. Let's do another problem. This problem is dy dt equals 1 plus t times 1 plus y. So let's do the same thing again. Let's move all the y's to one side. 1 over 1 plus y dy. Let's multiply both sides by t, dt, 1 plus t dt. And let's integrate both sides. When we integrate both sides, you see that on the left, we actually have a log of y plus 1. Now, a lot of people will write log of the absolute value of y plus 1. This in differential equations is sometimes needed, but oftentimes it is not. So I would recommend that you just leave it as parentheses. And then here, what do we have? We have t plus t squared over 2 plus c. Now, how do I solve for y? I need to solve for y by removing everything around the y. The first thing I remove is the log. And so what I'm going to do is we're going to do that by exponentiating e to both sides, right? So take e to both sides. What does that mean? That means I basically am going to make these expressions both exponents of e. In this case, the log and the e cancel each other out as we wished. Y equals 1 equals e to the t plus t squared over 2 plus c. And then finally, y is equal to e to the t plus t squared over 2 plus c minus 1. Consider the following one, which involves some amount of trigonometry. Cosine of y, sine of t, dy dt equals sine y, cosine of t. Right, so here's the idea here. Let's move the sign this way. Let's move that sign that way. Let's do that first. So I have a cosine y divided by sine y, dy dt equals cosine of t divided by sine t. And then I'm going to multiply both sides by t, dt, and I get, well, cosine of y over sine y is just cotangent of y. dy equals cotangent of t dt. And now I integrate both sides. The antiderivative of cotangent, remember that cotangent of u equals the sine of u, is the cosine of u over the sine of u. And so if you do a substitution, say, w equals sine of u, then the du is just on top. So the log of sine of u is equal to the log of the sine of t plus c. This plus c is very important. Now again, let's dispense with the absolute values around the log. This should be perfectly okay. So now let's take the e of both sides, because I want to solve for y. This is a y. I want to solve for y, so let's remove everything from the left little by little. Let's raise both sides to the e. So I have sine of y is equal to e to the log of sine of t plus c. Now let's clean this up a little bit on the right. I can write this as e to the ln of sine of t e to the c. And this e to the c is just another constant. And this e cancels out with that log. So sine of y is equal to sine of t times some other constant called a. Maybe we can put the a in front, a sine t. And then to solve for y, I just need to take the arcsine of both sides, the arcsine of a sine t. And that is the solution. You cannot simplify it anymore. And let me just give a warning here, right? The plus c is absolutely a requirement. It is a requirement at the moment of integration. So here's an example of how one might accidentally do it incorrectly. Suppose at this point you are here, right? So let me show this is an incorrect way of doing the problem, right? Suppose I say, oh, I'm going to integrate cotangent of y on this side. I'm going to integrate cotangent of t on this side. I get the log of cosine, the log of sine y equals the log of sine t. Now, suppose I decide, that I forgot, I just didn't feel like writing the plus c. I just left it out. Maybe I forgot. Okay. And then I e both sides, and then I get sine y equals sine t. And then you might say to yourself, oh, I'm going to take the arcsine of both sides. And so I get y equals t. Oh, and then I'm going to add the c at the very, very end. Okay. Right. Adding the c at the end is not correct. Right, is wrong. So this is not the correct solution, right? You have to add the c at the moment of integration and not after that. That's a really important thing to remember. So this is the correct answer and not this. So now we'll take a look at some so-called initial value problems. Initial value problems for differential equations is a differential equation with an added condition that allows you to solve for c. Allows for c to be solved. All right, so here's an example, right? So solve the initial value problem t squared 1 plus y squared plus 2y dy dt equals 0 with the condition that y of 0 equals 1. In addition, describe the interval of existence for the solution. And we'll see what this means when we get to it. All right, so let's first move. So we have this equation. Let's just write it down again. Plus 2y dy dt equals 0. Let's move this piece to the right. 2y dy dt equals negative t squared 1 plus y squared. Now let's get all my y's to one side, divide by 1 plus y squared, and multiply by dt. So I have 2y over 1 plus y squared is equal to minus t squared dt. Let's integrate both sides. The right side is easy. It's minus t cubed over 3 plus a constant. The right side is a u substitution. U equals 1 plus y squared. Du equals 2y dy. I have a dy over here. So I have just simply du over u. And then that integrates to log of u. And again, let's not worry about the absolute values. You'll see that we're not going to need them anyway, because if I plug in for u, I get log of 1 plus y squared, which is always positive, so I don't need absolute values around it. Now at this point, I can plug in for y and t and try to figure out what c is. So the initial condition says that y equals 1 when t is equal to 0. So I have a log of 1 plus 1, which is 2, is equal to c, right? Because this t cubed over 3 is 0. So c is log 2. So we can go back to here. Log of 1 plus y squared is equal to negative t cubed over 3 plus log 2. Now let's solve for y by raising e to both sides. And then the e cancels out with this log here, 1 plus y squared. And let's break this into 2, e to the minus t cubed over 3, e to the log 2. E to the log 2 is just 2. So I have 1 plus y squared equals 2 e to the negative t cubed over 3. Let's move the 1 over. Y squared is 2 e to the minus t cubed over 3 minus 1. Now, when you take the square root, officially, technically, you get a plus or a minus, the minus t cubed over 3 minus 1. But you see that y is a positive number at the initial condition. Y is equal to 1. So I take the positive root, okay? Square root of 2e to the minus t cubed over 3 minus 1. So this is the solution for the initial value problem. Now, the second part of the problem says, find the interval of existence. Notice, right, that in order for this solution to exist, the function inside the square root has to be positive. It has to be positive. So let's solve for t and see what t's render this expression positive. Let's move the 1 over. So I can move the 1 over. Now let's divide by 2. All right. And now I'm going to take the e of both sides. I'm taking the log of the ln of both sides. So this is minus t cubed over 3 is greater than log of 1/2. Now remember that log of 1/2 is the same thing as log of 2 inverse. And then the negative 1 comes down in front and becomes a minus log 2. Now I'm going to negate both sides. And when I negate both sides, the inequality flips this way. Let's multiply by 3. T cubed is less than 3 log 2. And at the very end, let's take the cube root. So t is less than the cube root of 3 ln of 2. So notice that t started out at t equals 0. So the interval of existence for this problem is 0t, the cube root of 3 log 2. And in fact, you see that we're actually allowed to be greater than or equal to 0 here. So we could, in fact, make all of these equality as well. So I can close this interval right here. And so that's the interval of existence for this problem. Let's try another initial value problem. This is problem 7. All right, so let's consider the following. Cosine of y dy dt is equal to negative t sine of y over 1 plus t squared, where y of 1 is equal to pi over 2. All right, so let's try to separate. Let's divide both sides by sine. Cosine y over sine y dy. Let's multiply both sides by dt minus t over 1 plus t squared dt. And let's integrate both sides. Now, this function right here is cotangent, and we saw earlier that the antiderivative of cotangent is just the ln of sine y. And then here, if I take a u substitution, u equals 1 plus t squared, then du equals 2t dt. So 1/2 du is t dt. Therefore, I have a minus 1/2 antiderivative of du over u. So I have ln of sine y. Oh, actually, let's make the initial condition y of 1 equals pi over 4. And I'll explain why I made that change in just a little bit. Equals minus 1/2 ln of u plus c. So ln of sine y is equal to minus 1/2 ln of 1 plus t squared plus c. Now, at this point, we could plug in our initial conditions and see what we get. So y equals pi over 4 when t is equal to 1. So I have ln of sine of pi over 4 is equal to minus 1/2 ln of 1 plus 1, which is 2, plus c. Now, what is ln of sine of pi over 4 is 1 over root 2. So that's equal to, okay, let's just continue writing this down, plus c. So c is equal to log of 1 over root 2 plus 1/2 log 2. Now, what does that mean? C is log of 1 over root 2 plus log of 2 to the 1/2. I can just move this 1/2 to this power up here, so I get log of root 2. And when I have a sum of logs, I get the log of the product, right? Using the formula log of AB equals log of A plus log of B. So then I get log of 1, so that's equal to 0. So C is equal to 0. Let's go back here and plug in C. So I have log of sine y equals negative 1/2 log of 1 plus t squared plus 0. Now, let's take this minus 1/2 and put it up here. So ln of sine y is equal to ln of 1 plus t squared to the negative 1/2. And then I can both sides. I get sine of y equals 1 plus t squared to the negative 1/2. So y is equal to the arcsine 1 plus t squared to the negative 1/2. And you can also write this as arcsine of 1 over square root of 1 plus t squared. So that's the solution. And notice you can only take the arcsine of a number that's between negative 1 and 1. So notice that this number right here is strictly positive. and it's less than 1. Well, I guess it's less than or equal to 1. So the arcsine of 1 over square root of 1 plus t squared is always defined. All right, so there are no restrictions on the domain. All right. So earlier I had made a slight adjustment with this equation, and let me explain why. What happens if we had done this problem right here? So in fact, if we do this problem right here, we would have gotten an answer a little bit similar to this, except for a slight constant change. But there's actually kind of a trick. If you notice that if I had plugged this in to the very beginning, y is equal to pi over 2 when t is equal to 1, right? Then I would have gotten cosine of pi over 2 dy dt is equal to -1 times sine of pi over 2 over 1 plus 1. The right-hand side is going to be a -1 over 2, but the right-hand side, the cosine of pi over 2 is equal to 0. So I would have gotten this. So this is, of course, nonsense, right? This is a contradiction. So what we're saying is that for this particular initial value problem, there is no solution. So this is sort of a cautionary tale that sometimes it might be helpful just to take a look at the initial condition and see whether or not it actually violates the initial equation to begin with. So a little bit of subtlety involved in these kinds of initial value problems. Now let's take a look at a problem that involves a little bit of a subtlety. Let's take dy dt is equal to 3t squared plus 4t plus 2 over 2y minus 1, where y of 0 is equal to -1. Now, this 2 is kind of interesting. It seems like the 2 can be left either on the right or the left, but let's see why putting it on the left is actually a good idea. So let's separate the y and the t. And here, let's take the antiderivative. Now, you might be tempted, for example, to rewrite this as 2y minus 2, and then take the integral and get y squared minus 2y, for example. But notice that there's another way to antidifferentiate this, and that is simply that the antiderivative is y minus 1 quantity squared. Because after all, when you take the derivative, you get 2 times y minus 1. So instead of integrating this piece by piece and getting a multitude of y's, notice that if you just integrate it this way, the y only appears once. So here I can anti-differentiate, and with that, now we can actually impose our initial condition, y is equal to -1, and t is actually equal to 0. So in this case, I get a lot of 0, 0 plus 0 plus 0 plus c. And here I get a -1 minus 1, so I get a -2 squared. So c is equal to 4. In this case, let's go back to y minus 1 quantity squared is equal to t cubed plus 2t squared plus 2t plus 4. And then I'm going to take the square root. So it's going to be plus or minus t cubed plus 2t squared plus 2t plus 4. Now, let's take a look at which branch I should take. Notice that y is -1. So that means that right here, when t is equal to 0, y is equal to -1, I actually get a negative number here. And so I really need to make sure that the right side is also negative. So my minus 1 is equal to negative t cubed plus 2t squared plus 2t plus 4. And finally, I'm going to bring the 1 over y. It's 1 minus square root of t cubed plus 2t squared plus 2t plus 4. And that is the solution for this initial value problem. So now let's work on these so-called initial value problems. These are problems where you are given an extra condition that allows you to solve for c. So here's an example. T squared 1 plus y squared plus 2y dy dt is equal to 0, and our initial condition is y of 0 equals 1. So let's try to separate variables. Let's move this guy to the right side. 2y dy dt is equal to 2 squared times 1 plus y squared. Now let's try to move all the y's to one side. So divide by 1 plus y squared and multiply by dt. So we have 2y over 1 plus y squared dy is equal to t squared dt. And now let's integrate both sides. Now the right-hand side is simple. It's 1/3 t cubed plus c. And the left side is also not so hard. You can set u equal to 1 plus y squared, then du equals 2y dy. So then my integral is really going to be du over u. And so this is simply log of u equals 1/3 t cubed plus c. And u, let's just replace u with 1 plus y squared. That's 1/3 t cubed plus c. Now, at this point, or at any point, once you have an equation involving y and t, after the integration, you can plug in this information right here. Here, we're going to have y equals 1 when t is equal to 0. So when y is equal to 1, t is equal to 0, I get a log of 2 equals c. So that's what c is equal to. So that's log of 1 plus y squared equals 1/3 t cubed plus log of 2. Now let's try to solve for y. I'm going to take both sides to the e to the both sides, right, with base e. So I have an e here and then I have an e here. So the e and the log cancel each other out. So I have a 1 plus y squared is equal to e to the 1/3 t cubed. I'm going to separate this e to the log 2 because e to the log 2 is just simply 2. So this number right here becomes a 2, so I get a 2e to the 1/3 t cubed. And to solve for y, I subtract 1, 2e to the 1/3 t cubed minus 1, and then I take the square root, y equals the square root. Right, now let's put the plus or minus here first and then see what happens, right? Okay, so notice here that when t is equal to 0, right, when t is 0, y is equal to 1, right? So when t is equal to 0, y is a positive number. So as a result, I take the positive root and not the negative root. So this is the solution to what's called the initial value problem that we had at the beginning. So now let's do some examples in which the answer is going to be left in what's called implicit form. This is a case in which you can solve for c but you cannot explicitly solve for y, but cannot explicitly solve for y. So here's some examples. The first one is, let's consider dy dt to be t squared plus 1 over 1 plus y to the fourth, with y of 0 equals 1. Now, in this case, if I separate, let's put all the y's on one side and all the t's on the other side, and then I integrate both sides. You see here, I have y plus 1/5 y to the fifth, and on this side, I have t cubed over 3 plus t plus c. Now, at this point, I can stick in the initial condition, y equals 1, t equals 0. So I get 1 plus the fifth equals c. So c is equal to 6 over 5. And therefore, going back up here, I have y plus 1/5 y to the fourth, y to the fifth is equal to t cubed over 3 plus t plus 6 over 5. But notice here that, y shows up twice. And this is an equation for which you cannot solve for y explicitly. So here, we cannot solve for y explicitly. So we leave it in what we call implicit form, which is exactly this formula. That is where you end. Let me give another example in which this would happen. dy dt is equal to t cosine y, with y of 0 equals pi over 3. So in this case, let's move the cosine over to the other side. 1 over cosine y dy equals t dt. And this is secant y dy equals t dt. Let's integrate. The antiderivative of secant is log of secant t secant y plus tangent y. You can use absolute values or not. And on this side, you have t squared over 2 plus c. So when y is pi over 3, that means that t is equal to 0. So let's plug it in. Log of secant of pi over 3 plus tangent of pi over 3 is equal to 0 plus c. So what is c equal to? Log of secant of pi over 3 is 2. And the tangent of pi over 3 is root 3. So that's the value of c. And then I can go back here and write log of secant y plus tangent y is equal to t squared over 2 plus ln of 2 plus root 3. And you can leave it in this form. Perhaps you wish to take one more step, right? You can actually take e to both sides, and then I have secant of y plus tangent of y equals e to the t squared over 2, e to the ln of 2 plus root 3. So secant of y plus tangent of y is equal to, well, these cancel out, 2 plus root 3, e to the t squared over 2. But you still can't solve for y, so still cannot solve for y. So we leave it in this form. So far, we've been working on indefinite integrals. All right, we have been solving using indefinite integrals. And then once we solve using an indefinite integral, so we get a plus c, an unknown constant, and then with that unknown constant, an unknown constant c, and with an initial condition, we can solve for C. But now we're going to look at a way to do the problem with a definite integral. So separable equations solved by definite integrals. All right, so let's take an example. Let's consider dy dt is equal to 2t times y plus 1 with y of 0 equals 3. So this guy is separable. I can take dy over y plus 1 is equal to 2t dt. And now what I'm going to do is I'm going to integrate, right? Integrate both sides. But first of all, what I'm going to do is I'm going to integrate on the left, we will be integrating from y0, which is the initial condition for y, up to y. And on the right, I'm going to be integrating t0 to t. Now, one thing that you have to be careful about is suppose we integrate this from y0 to y. I don't want a y here and a y here. I want to change the variable for the integrand. So what I want to do first is change the equation, right, to say dw over w plus 1 is equal to 2s ds. So in other words, I'm changing t to s, and I'm changing y to w. And now I'm going to integrate. On the right, on the left, I'm going to have y0 to y of dw over w plus 1 is equal to t0 to t of 2s ds. Now here, what are y0 and t0? Here, my initial condition gives me a t0 is 0, and then y0 is 3. So I'll be integrating from 3 to y, dw w plus 1 is equal to 0 to t of 2s ds. So on the right, on the left, we have log of w plus 1 from 3 to y is equal to s squared from 0 to t. And so I can plug this in, log of y plus 1 minus log of 4 is equal to t squared minus 0. And so let's solve for y. Let's move the log 4 to the other side. And then let's take e of both sides. So I have y plus 1 is equal to e to the t squared, e to the log 4. So y, well, this is a 4. So I have a 4 e to the t squared, and then y equals 4e to the t squared minus 1. So this way, you don't actually have to solve for C. The constant is solved in the process of this problem. Let's do another example. Consider the differential equation dy over dt is equal to t e to the t over y plus 2 with the initial condition y of 0 equals 3. This problem will require an integration by parts, so it's worth reviewing that. Let's separate y plus 2 dy is equal to t e to the t dt. Now we're going to change y to w and t to s. So I have w plus 2 dw is equal to s e to the s ds. And now what I'm going to do is I'm going to integrate from y0 to y. of w plus 2 dw is equal to t0 to t of s e to the s ds. Now here, with the initial condition, y0 is equal to 3 and t0 is equal to 0. So I'm going to integrate from 3 to y of w plus 2 dw is equal to the integral from 0 to t of s e to the s ds. Now, on the left side, let's be smart, right? I mean, you could integrate this as that, right? But that actually turns out to be a bit of a mess. One other way to integrate this is just to treat this as one object and write 1/2 of w plus 2 squared. This is a lot cleaner. And here I have an integration by parts. S e to the s minus e to the s from 0 to t. All right, so I have 1/2 y plus 2 squared minus, let's plug in a 3, so I get a 25 over 2 is equal to t e to the t minus e to the t. And when I plug in a 0, this disappears, and then I get a -1. So let's clean this up a little bit. 1/2 y plus 2 squared. Let's move the 25 over 2 to the other side. T e to the t minus e to the t plus 1 plus 25 over 2. And then we're going to, let's add those constants together. Equals t e to the t minus e to the t plus 27 over 2. Let's multiply everything by 2. Y plus 2 squared is equal to 2t e to the t minus 2 e to the t plus 27. And let's take the square root. Y plus 2 is equal to the square root of 2t e to the t minus 2 e to the t plus 27. Notice that my initial condition says that y0 is equal to 3. So when y is equal to 3, I need a positive number. So even though I have a plus or minus here, I'm going to take the plus. Y is equal to the square root of 2t e to the t minus 2 e to the t plus 27 minus 2. And that's the final answer.